For this video, we're going through the wonderful world of acid and bases. It's a complex and wonderful place. Uh, where we are with these videos, you should understand what an acid and a base look like. You should be able to recognize acids and bases. The generic version of an acid is a Ha or a Choo-Choo. You should know the metal hydroxide or a Mu, and also ammonia or organic amines. You should know how they function in terms of Bronsted and Arrhenius. You should be able to go around through the Pang square, and if I give you a concentration of an H plus or an OH minus, be able to calculate pH. And you should be able to recognize a weak acid and weak base. There's 6 strong acids, the rest are weak. All Choo-Choos are weak. There are alkali hydroxide along with barium hydroxide. The rest of the metal hydroxides, which would be a lot, are weak, and that means ammonia and all organic amines are also weak. To round this off, you also need to recognize conjugate pairs. So a bit of review on looking at things or recognizing what they are. The first thing we have going on up here is going to be a weak acid, a generic weak acid right here. Examples of that would be like HClO or some kind of Choo-Choo. These are weak acids. They can work by Arrhenius, which means it drops off a hydrogen ion and you don't need water. It can work by Bronsted, in which you put water in as reactant and it drops a hydrogen ion off to the water to make a hydronium ion. This one is monoproduct, and that's the hydrogen, and this one is monoproduct, and that's the hydrogen. And these are not ionizable hydrogens over here. So when you have an organic Choo-Choo, only one hydrogen is ionizable, and it's the caboose, of course. Then once it dissociates, it forms a conjugate base. Conjugate pairs are always opposite. So if it's a weak acid, it's a conjugate base. If it's a weak base, it's a conjugate acid. We're going to learn how to recognize these things because if you have a conjugate base like A minus, and only that, it will act like a base, and therefore the pH is above 7. So if you put in just the perchlorate ion or just the ethanoate ion, which is in AP is going to be the acetate ion. You put this in, you have to recognize these as a generic A minus, and A minuses will hook up with pluses, and what's plus in water? It's going to be an H plus, and what is that left over as a production? An OH minus, pH is going to be above 7. If I wrote this equation on the screen. Now what we're working toward is to recognize that these will be aqueous. This is going to be a liquid, which does not go into the expression. We're going to have 2 things on top and 1 thing on the bottom. Since we're solving for OH minus, we'll need Kb because this is a conjugate base and it's mostly is producing an OH minus. The way you get the conjugate, the way you get a Kb is from the Ka, and Kw divided by the weak acid or base constant gives you the conjugate base or acid constant. So, which means the stronger the acid, the weaker the base, and the stronger the base, the weaker the acid when we're talking about conjugate pairs. This is all about recognizing things. We're writing chemical equations, not math equations. So the next one is just a base. This base is considered to be a Bronsted base only. It's going to be ammonia or some kind of organic amine. We talked about this in class that this is a trigonal pyramidal type of a structure. The nitrogen is right here in the middle, which causes the big time and negative end over here. And the big time negative end will hook up with an H plus, leaving you an OH minus left over, and that's how it makes a base. So that's the function of it. You could just memorize that you add an H plus to the bases, whatever works for you. So if we have NH3, we have to recognize that's a base just by memorization. When they hook up with water, it forms an equilibrium to form the conjugate acid, and the hydroxide ion, which makes the pH above 7. Again, two things on top, one thing on the bottom. Water doesn't go into it. It's producing OH, so we would need Kb. And since this is a base and not a conjugate base, they would flat out give you the Kb for it. After we have the base and those equations, now we have the conjugate acid. So you have to recognize that this came from a base and therefore it's an acid. This came from a base and therefore it's an acid. The dead giveaway is conjugate pairs are charged. So looking for the charged pieces, we can tell that they're conjugate. And again, we could think of conjugate as being the opposite. When we write an equation, we can write this equation three different ways. The easiest way is to write this as an Arrhenius acid. An Arrhenius acid will just drop off a hydrogen ion by itself like that. If we do this, we have two things on top, one thing on the bottom. It will equal to a Ka because we're producing hydrogen ions. Since this is a conjugate pair, they will give us a Ka. They'll give us a Kb for NH3. Well, the way we solve for Ka given a Kb from the conjugate is to have Kw divided by the given K value, and that's how you figure it out. If you're given the Ka and you want a Kb, well, divide Kw again by Ka to equal Kb, because Kw equals to the Ka of a weak acid times the Kb for its conjugate pair, and it doesn't matter which one's which. Again, there's three ways to write this equation. You could write water as a reactant. If you wrote water as a reactant, again, this would be a liquid. It wouldn't go to the expression. So you still got your basic two things on top, one thing on the bottom. And this would be a hydronium ion, but we treat hydronium ions and hydrogen ions as the same thing. We could also think of this as opposites attract, and we could put in the hydroxide onto the positive because they attach, and you'd end up with NH4OH, but you still end up with the H plus. You would still have one thing on the bottom, two things on top. We would still have the H plus as a product. Therefore, we will still need the Ka. They still won't give us the Ka. We get the Kb and divide it into the Kw. You don't have to memorize any K values. You do need to know relative strength. So since the equation is going to be Ka times Kb equals to Kw, if you have a stronger base than the acid, then the conjugate of the stronger base will be a weaker acid than the conjugate base of the other one. And we certainly can look in terms of powers in 10 to figure out which one's bigger. 10 to the minus 5 is bigger than 10 to the minus 6, that kind of thing. All right, moving on from this, we're going to look at salts. Salts are confusing because there's two things and we think it's something completely different. However, they're not. Here we have an A minus. We said a minute ago that because it's charged, that's a conjugate pair. It comes from a weak acid and therefore it's a weak base. Weak acids and bases never make strong acids and strong bases. So that's not something new. We just have to come back over here and recognize the pieces that might be coming off of a salt. And if this is the conjugate, they would produce, that alone would produce a pH above 7. The other one's can be a little trickier. First of all, you could form, some kind of methylamine or possibly ammonium, and therefore this is the weak acid conjugate pair of the weak base. It can also produce a metal, which we're not used to. But again, we can go back to our middle school and recognize that opposites attract. And if you have water here, this is a positive, the aluminum is, it will hook up with water to form AlOH3, and then what you have left over are going to be 3 hydrogen ions. Now this won't go to completion, it'll be a equilibrium. But still, if you're producing H pluses, that means this is a weak acid because it doesn't go completely and you're producing H pluses. So this concludes this video because it really is just trying to get you to recognize the pieces. If you can't recognize the pieces when it gets complicated with buffers, or if you put a salt in it, or heaven forbid, you put a strong acid or a strong base into a buffer, you're not going to understand how this functions in water and how the reactions are going to take place. And if you can't do that, you really can't do the math. So make sure you go through this video more often. If you need more examples, let me know.